Okay, yeah. Very happy to talk here. I'm going to start with the data set that some people in the room actually know. This is the amygdala data set that was published in a paper by Tawakul and others in 2017. And some people very strongly connected to this group, like Noah as the first author, put together a paper where they had 4 different teams of statisticians analyzing this data set. The issue there is whether perceived stress is positively associated with resting activity in the amygdala. I'm an expert for none of these things, right? I was one of the statisticians who analyzed these data together with Daniel, actually. We have measurements from 13 individuals who were all volunteers with post-traumatic stress disorders, and the data look like this, right? So you have a perceived stress scale and you have amygdala activity, and these are your data. So in the original paper, they tested the null hypothesis that the correlation between these two, the true correlation between these two variables is 0. Against the alternative that it's not 0. In order to do this, they actually computed the Pearson correlation coefficient that looks like this, most scary formula in the whole presentation. They assumed, so if you assume the pairs of observations x1, y1, so that would be pairs of stress score and amygdala activity, and n is the number of observations. If you assume all of these independently identically distributed, which I call IID, according to a bivariate normal distribution, then one can show mathematically that this animal here is distributed according to a t-distribution with n-2 degrees of freedom. And based on this, one can actually, one can compute the R, which is the sample correlation coefficient. That's 0.56, right? It looks like this goes up here. And you can test the null hypothesis, and the t-distribution gives you a p-value of 0.048. You can also compute a 95% confidence interval for the correlation that runs from 0.01 to 0.85. And in the paper, Tawakul and all state, basically making reference of this p-value that is just about smaller than 0.05, that the perceived stress was associated with amygdala activity. Now, this is based on this model assumption here, right? And actually, Tawakul and others in this paper literally state that these variables were normal, suggesting in turn that the model assumptions were fulfilled. Let's have a look at this. So the first thing is, we only have 13 observations. If we look at the data, the statistician would say, regarding bivariate normality, there's not much of a concern, right? Data can look like this. That's not a problem. But of course, with 13 observations, not much can be seen in the data in the first place about the distributional shape. Then the next thing is the paper has actually no information about independent identical distribution. Particularly, I have no idea whether some of the test persons knew each other and maybe discussed stress among themselves, or whether there were any meaningful grouping of the test persons that should also have an influence on the results. And in fact, it's even worse, right? No normality is violated because the variables, the amygdala activity measurement and the stress scale are defined in such a way that they can only take positive values. Normal distribution has a non-zero probability for negative observations, and nothing that cannot have negative observations can ever be normally distributed. Then also, famous Buddhist Vietnamese monk Thich Nhat said, everything depends on everything else. I tend to agree with this, right? And then the famous statistician George Box says, all models are wrong, but some are useful. We maybe agree on the first bit, and the second one we can ask about this one. Okay, good. So what is going on in statistical modeling, right? So we are interested in a bit of reality, which you can see here. For example, we can be interested in measuring the quality scores of bad drawers, right, which is what is illustrated here. We have some measurements, we replicate some observations, and when the statistician comes in, what the statistician does is this, right? So the statistician thinks about the data in terms of like a mathematical model that has some parameters, mu and sigma squared in there, and basically assumes that this produced the data, right? And then the statistician may ask, what is the true mu and what is the true sigma? And then there are methods that help the statistician to find this out, right? You can estimate these numbers. And given these numbers, basically, okay, well, this addresses the question. We have some guesses for what goes on up here, right? That's pretty clear. What is by far not so clear is what is the relation between this and this, and in turn, what is the relation between this and this? And this is what I'm going to talk about. Statistical inference is based on mathematical reason in the model world. The model world is essentially different from the real world, right? You can see this very easily in my drawings. Data connect the model world and the real world, but it's far from trivial to understand what model world results mean for the real world. Now, here's something that many people think and say, and that even statisticians say a lot when they teach statistics. Model-based statistical inference is valid if and only if the model is true. This is misleading. If we were like this, we could not do any statistic at all, right? It's not the job of models to be true. Models are tools for thinking. So what is the job of models then? Why do we use them? Well, the first thing is they are actually required for handling the observations mathematically. We can use proved mathematical theory, and we hope that we therefore get secured results that we also can sell as being objective. We can actually quantify uncertainty, which we can't do if we don't use models, right? And we can also make quantitative predictions that can actually be tested. We can also do other things. Namely, we can set up models in which we can control the truth, because it's all of our building, right? And use this to theoretically assess the performance of methods, and in turn, to actually inspire method choice, right? Many statistical methods that we use actually have fallen out of theories that describe some optimal results, optimal performance, assuming certain models. And then something that people don't talk about a lot, we can also use models for an unambiguous communication of points of view, because the mathematical symbols, although difficult to manage for many, are actually have a very high degree of unambiguity. And then also, and this is one that I like a lot, we can learn from deviations from models. So we can actually use the fact that they are wrong. These were the results, right? These relate to an IID bivariate normal model. And what do these results mean in practice? Well, as long as we are willing to think in terms of the model, they can actually really mean quite something. So, for example, if you look at this, you can see at the 95% level that although you have a p-value that is smaller than 5%, actually you have a confidence interval that has very, very low values of correlation in it. Depending on the application, you could say, well, for sure, there's no meaningful evidence for a reasonably large effect, because the data that we see are very well compatible with 0.01 or 0.1 or something. And also, it says that we really don't know very precisely where the correlation is. But actually, the model doesn't hold. And what are the implications of this? Before I come back to this, I'll talk a bit about errors, right? Because this is a scientific error workshop. So errors and frequentist statistics. Traditional definition of errors, right? There's a type 1 error, which is that we reject a null hypothesis that is true. That would be false positives, right? Type 2 error, we do not reject a null hypothesis if it's not true. That would be false negatives. And also an error in confidence intervals is that the confidence interval does not catch the true value, which is all defined in terms of the model, right? But as a model, the null hypothesis is never true, and neither is the alternative, or actually any parameter value that is defined by the model. The traditional errors of inference actually live in the model world. So if people come and say, oh, we have false positives here, false negatives there, and we talk about statistical testing, it's not really clear what that means, because that's about reality, and reality is not a model, right? So what constitutes an error in inference with real data? Here I introduced a strange word, this strange concept that I would like to use to discuss this. So we have an interpretative null hypothesis. That's basically a sentence that makes reference to what people think of as the real world, right? Amygdala activity is not associated with stress levels. And then the interpretative alternative amygdala activity is associated with stress levels. And then we can define interpretative type 1 error and interpretative type 2 error, right? So this would be reject the null hypothesis if the reality behaves like what we think the interpretative null hypothesis is. And the type 2 error, right, do not reject the null hypothesis if reality behaves like what we think of as the interpretative alternative. So this is what the researcher would really be interested in, which of course is in terms of reality, not in terms of the model, and correspondingly also for confidence. I gotta say, but this is just a side remark, even the assumption that reality objectively behaves as if either the interpretative null hypothesis or the alternative is true is questionable, right? It's no more than a working hypothesis here that can help me to define the concepts. Now, if you look at these, one thing is there's no normal distribution in this, and there's no IID assumption in this, right? The statistical assumptions do not feature here. Unfortunately, we need such assumptions to quantify the uncertainty and the method performance. So I'm now talking about modeling what happens if we are not in the model. So if we are curious about how the test performs if the nominal model doesn't hold, so for example, to compute error probabilities, we need to define what an error is, meaning when we actually should reject the null hypothesis and when we shouldn't. And this is normally only defined within the nominal model, right? So it amounts to deciding what parameters are assigned that we would interpret as null hypothesis and alternative. However, let's go at this in a more bolder way, right? Let's say the interpretative null hypothesis and alternatives are all distributions that can happen that actually would model the real unformalized null or alternative hypothesis of interest. I want to promote here the awareness that the real hypotheses are informal and could be modeled by many distributions. So this would amount to modeling that the model doesn't hold. Of course, you may question whether any models, frequentist models of this kind, hold. But for benefiting from modeling, I will not drop this, right? I will still use them, not because I believe they are true, right? That's not the job of models. So basically, we have a set that has all possible models with dependence, non-identity, other distributional shapes that are conceivable for the situation in which we are. And I mean, the null hypothesis and the alternative are really only a very small part of this. And then what I'm saying is, well, I kind of allow for things that are kind of weird, where you cannot really say, okay, if this is the case, then I believe amygdala activity and stress are related or not. But there are large parts of all possible models where we'd say, well, if this kind of stuff happens, we would basically say there's no effect. And if this kind of stuff happens, we would basically say there is one. So that would be, in fact, the null hypothesis and the alternative we are interested in. Now, making sure we understand that this is, we gotta have to decide all kinds of situations, right? For example, what you see here is you see a distribution of data where X and the Y actually have a correlation of 0, but there is dependence, right? There is such a squared relation. And we got to decide, does this belong to the interpretative null hypothesis or not? So here, actually, you would expect a correlation test would not normally reject, because if the X variable grows, the Y variable neither goes systematically up nor down, but it changes systematically. So an independence test will. And what do we actually want? Is this a case for rejecting our interpretative null hypothesis in which we are interested or not? Other example, so we have a large majority of probability for a group where there's a clearly positive correlation, yet if we put this together, we rather have a negative correlation. What is it, what we're interested in? Are we interested in the majority group only? Are we interested in what we get if we put them together? Or are we interested in saying, well, in a situation like this, the situation is ambiguous and I don't want to decide either. And these things need judgment, right? The data cannot decide this. The data are not going to say what kind of hypothesis we put where, and neither can mathematics, right? This is really a subject matter decision and not always easy. Then there's another thing, there's interpretative similarity under the nominal model. You probably know that tests of point null hypothesis are often criticized for rejecting a null hypothesis if the sample size is too large in presence of substantially meaningless deviations from the null hypothesis. Now, in fact, even in this situation with only 13 observations, the authors reject correlation equal to 0, despite the fact that there are very, very low values in the confidence interval. And this is a problem because the test ignores that parameter values very close to the null hypothesis are often interpretatively more similar to the null hypothesis than to the alternative. And in order to deal with this, we need to consider effect size, severity, and others to not misinterpret the rejection of the null hypothesis. In this picture, by the way, I drew it in such a way that something that formally belongs to the alternative right here is still part of the interpretative null hypothesis, where we would say, well, actually, if the correlation is very, very low but existing, we would not want to reject, and it would be a problem if we did. Okay, so now I'm going at it from the side of the test. What do tests actually do if we don't take the model assumptions for granted? Tests are defined usually by a rejection region Q, right? So if the observation falls into Q, we reject, otherwise not. And I call effective null hypothesis the space of any probability measures for which the probability to reject is smaller, actually I should have, smaller or equal than alpha, where alpha is the significance level that we're going to use. And the effective alternative, any probability measure for which the probability to reject is large. Now, this provides a non-parametric definition of a test that originally might well be parametric, right? So I used the same test, but I say this is what the test does if we do not take the model assumption for granted. Note, by the way, that there may be probabilities, or certainly there are probability measures where the probability to reject is larger than alpha, but still small, right? So the test will reject more easily than under the formal null hypothesis, but it can't be expected to reject because it won't do that very often. And such distributions are in a gray area with respect to the test. So actually what we have here is the green thing is what I call the effective null hypothesis, right? That would be the set of distributions for which the probability to reject is very low. The effective alternative, where we expect to reject, in this gray area where the probability to reject is not low, but also not very large. Now, let's go back at this, right? So we have a t-test that is based on this statistic here. What it will do is it will reject the null hypothesis if the absolute value of the Pearson correlation is larger than some constant. This can be interpreted as testing the general non-parametric effective null hypothesis that there's any distribution underlying this such that the probability to reject is very low, against the effective alternative, any distribution underlying this such that the probability to reject is large. And the key issue then is, does the definition of the test indicate the desired direction of deviation from the interpretative null hypothesis? Which is different from what usually people ask, namely, are the assumptions fulfilled, which they are not, right? We know that even before testing. So we got to look at this and try to understand what it does and whether this properly formalizes what we are interested in. And this amounts to understanding whether R is aggregation of the information in the data is interpretatively correct, which means that the effective null hypothesis and alternative would correspond well to the interpretative null hypothesis alternative. And I mean, this is a complicated discussion. I'm not going to go into it in any detail. Lots has been written about the effect of gross outliers on correlation and generally normal distribution-based theory, which can break down. Also, we can be interested in the behavior and the relevant dependence patterns and so on. Statisticians tend to think of these statistics as optimal under certain models, but they have a data analytic meaning on top of it, and this is crucial to understand for use in inference without taking the model for granted, right? So what we basically would like to achieve is that the green region here and this are the same, and the other green region here and this are the same. And unfortunately, this is so complicated that we can't have perfection, right? But so it's basically a framework for thinking about this. Okay, how can mathematics help us, and how can mathematics lead us astray? So obviously, standard use of mathematics for statistical models allows us to specify methods that can be proven to work well or even optimal. It allows to quantify uncertainty in a well-defined manner, all assuming that the model holds, right? What happens to the methods if the model is not true? Mathematics or simulations, which is basically kind of experimental mathematics, if you want, can tell us if we model deviations from the assumed nominal model, what happens? So we can derive what our method will deliver, even though a model deviation from the nominal model isn't true either, right? But we model deviations from the model, right? Lots of stuff can happen, not only this. So, for example, one can show by simulation, at least, that if we model data as truncated normal without negative values, or with certain easy patterns of correlation between observations, and then we can compute the distribution of R, and we then ask the question, does it still have roughly the same characteristics as under the nominal model? And I mean, if you truncate the distribution at 0 here, and here you see the data on quite some distance of 0, if you look at normal distributions compatible with that, you basically find out that that is not really a big problem. It is not really a big problem if most of the distribution is far away from 0, which it kind of is, right? There's quite a bit of space here. On the other hand, correlation between observations can increase the variation of the test statistic a lot. And unfortunately, this cannot be detected from the data. I mean, some correlation can, but very simple and problematic correlation structures cannot. So now, if we look at these theories, we tend to do some tentative conclusion or interpretation, and these are problematic. So, for example, we tend to think if the truth is close to the assumed model, the distribution of T, if T is the statistic of interest, will be close to the assumed one. Unfortunately, that's not necessarily the case, and it also depends on the exact formal definition what close actually means, right? So, for example, it's well known that if you have a model where you have a large probability of observations from a normal distribution and then low probability of gross outliers, you can have really very different behavior in inference. On the other hand, if the data look like typical data generated from the assumed model, you can think that the distribution of T will be close to assumed. That's not necessarily true either, because correlation can spoil this. On the other hand, you could think if the assumed model is clearly violated, the distribution of T will be very different from what is assumed. That's not necessarily true either due to the central limit theorem. So actually, we need to understand which violations of the assumed model lead to problems and which don't. And unfortunately, standard tools for this, like misspecification testing, are not very good at that. Always, this is known from 1944. We have written a survey paper about this recently. So we need to look at the data, but also take into account all kinds of background information that we find to know potential issues that the data won't show. We will never be safe, right? Model-based statistical analysis is kind of like this, and there's the general. I'm actually not quite as fast as I was thinking, so to leave some space for discussion, I think I skipped this, although this is also very nice and interesting. So I basically introduced the idea of interpretative and effective hypothesis.
Christian, you have until 3 in total with questions, right?
Oh, I have until 3.
With questions until 3.
So I thought until 2:45.
No.
Good. No, then you get this too. Yeah, I was kind of surprised because I thought it goes very smoothly. And then I looked at this and I thought, only 4 minutes left.
No.
Now I waste time in this way. Okay. So, one thing that is also important here is that is the role of mathematics, right? Mathematical statements are proved uncontroversial and can be taken as objective. And obviously, objectivity, we have discussed this yesterday already, is a key aim of science. So this leads to the temptation to identify the reality with mathematics and to take mathematics as saying more about reality and science than it actually does, right? And mathematics does not say how reality really is. Neither does it say what a scientist should do. What it does is it can characterize what we are doing, and what to make of the characteristics is context dependent, and the context is not fully in the mathematics, right? And so here are some statements that people can get from mathematics and how they are often misinterpreted. So, for example, Nyman-Pearson theory will say that a certain test T is optimal for testing a certain null hypothesis against an alternative in a specific model setup. So misinterpretation 1 is, so test T is optimal in reality, which we don't know, right? It's not even clear what that means, by the way, although I tried to define that a bit. The misinterpretation 2, either the null hypothesis or the alternative is true in reality. But actually, they are only very small classes as far as they're formally defined. Misinterpretation 3, we have to make sure the model is true. Well, we could pack it if that were the case, right? No, we have to live with the fact that it is not. That is actually what counts. On the other hand, misinterpretation 4, as the model is not true anyway, the test is not informative. Well, if that were the case, mathematics and science would be over, right? That's not. But you read all these arguments against models some people come up with. This particularly against significance tests. Next thing. If we want to do mathematical theory about the optimality, but also about the proper performance of a test in a model, we basically frame it as binary decision problem. So misinterpretation could be that binary decisions should be made in practice, right? You should kind of accept or reject a null hypothesis rather than basically understanding whatever you do as a small step in a bigger building up general evidence to make more differentiated statements. And then test T can reject the model of no effect against an alternative model of effect. Misinterpretation 1, so this is mathematics, right? It's necessary to reject no effect to say anything valuable. Misinterpretation 2 would be it is sufficient to reject no effect to say anything valuable. So all of these, I think, kind of try to draw some authority from the mathematical theory behind it, but really none of these misinterpretations is actually in line with the mathematics and what mathematics is actually saying. Okay, final remarks now. I basically introduced these ideas to explain the workings and interpretation of inference in a fully general model plus. Unfortunately, I got to disappoint you. I don't have a smooth theory to deal with this, right? And actually, it's too complex to handle mathematically because the full set of all conceivable distributions is just too big. So I'm creating problems here, and I'm not solving them. What one can do is one can do theory and simulations for exemplary models, so exploring specific situations one is interested in. I showed some examples for this earlier, and which also can go under the flag of sensitivity analysis. Some people may say, well, you are lost when you start with frequentist inference in the first place, right, like tests. I don't think that's the issue. The model is not true. Issue is just the same for Bayesian statistics and all kinds of other approaches. In the literature, there are robust and non-parametric methods. And actually, I like many of them, right? They can improve the link between effective and interpretative hypothesis. So I'm not saying that everybody always should assume normal distributions or something, but they can't solve all the issues, right? The user shouldn't feel too safe. They still assume IID. They can perform worse in some specific situations. The traditional frequentist inference errors are idealized model-based concepts and have their legitimation as such, right? They get theory going, and I have no issue with that. And what I did here was a reformulation in terms of interpretative hypothesis. I should say that still looks a bit more binary than I do this because it helps to clarify concepts. I do not generally recommend that people should think binary in statistics, right? But we always simplify, and this is one. The fact that the model doesn't hold is not an error, because that's not what models are there for. On the other hand, ignoring potential differences between model and reality, that looks erroneous to me, as do misinterpretations of theoretical results and overconfident interpretation and suppressing model uncertainty. And that's it. Thank you very much.